We will here look at some geometric results that follows by using trigonometry. So we'll have some theorems here we'll consider. And the first theorem we have is the following. Here we have a triangle, but it's not a right triangle. So these theorems we now will consider doesn't really limit itself to right triangles. It could be any triangle. But still, the results are trigonometry. If you have a triangle like this, one side is A, other side is B, and the angle between them is V, then it follows that the area of this triangle is equal to 1/2 A times B, but then sine of V. Let's take an example of this. So if we have a triangle looking like this, an angle of 20 degrees here, and then lengths of 8 and 10, then we can just use this formula. So the area of this triangle is 1/2 times 8 times 10 times sine 20 degrees. Now, sine 20 degrees is not a typical angle like 45, 60 or 30. So we can use a calculator. So we can take an approximate value of this one, and that will be 0.34, keeping 2 decimals. So this we can round off to 13.6. So we can just basically use calculator to calculate this, and we keep 1 decimal, we get 13.6. So the area of this is 13.6 area units. So if this is in meters, then of course it's square meters. Let us now prove this theorem here. If we have an angle smaller than 90 degrees, the triangle can look either like this or like this. So in these two different ways. In either case, we have that sine of V, that's this height, or in this case, this height, because here we have a right angle triangle. So it's H divided by A here, and here is also divided by A. So in both cases we have it like this. And here we could rewrite this as H is equal to A times sine of V. And that means that the area of the triangle is the base, or the base here, times the height. And the height we have here. But then it should be divided by 2. But this is just, we can rewrite as this. And then we have proved the formula. Then we just have to consider the case when the angle is 90 degrees or larger than 90 degrees. If V is 90 degrees here, then of course it's very simple to calculate the area. Just take the base times the height and divide by 2. But if you remember now that sine of 90 degrees, what is that? Well, we can take out our unit circle. So sine 90 degrees, then we are here, up here. So we have 90 degrees here. And what is the y coordinate of this point? The x coordinate is 0 and the y coordinate is 1. So sine 90 degrees is equal to 1. Okay, so sine 90 degrees is equal to 1. So we can write here, of course, it doesn't matter, we write the 1 here. But we know that 1 is equal to sine 90 degrees. So I can write this as AB times sine 90 degrees. And this is just now the formula we had. Just this formula, with a special case when V is 90 degrees. So the formula also works when V is 90 degrees. So now it only remains the case where to prove what happens when V is larger than 90 degrees. In this case, the triangle looks like this. So for V larger than 90 degrees. So we have A, B and the angle, and we have the height here. this angle here, let's call that W. And so W plus V is 180 degrees. So we have that sine of W, because here we have a right triangle, so we can use here a trigonometry. So what's that? Yeah, for this triangle it's H divided by the hypotenuse, but that's A. Okay, so we have like this. Then we can write this as H is equal to A times sine W. But sine W, that's the same as 180 degrees minus V, since these two add up to 180 degrees. But then what is sine 180 minus V? Let's take our unit circle here. So we have V here. And then we have, if we take the mirror image of that, like this, then we also have V here. And these are at the same height for symmetry reasons. Okay, so this is V. What is then 180 minus V? Yeah, that's this. So this is this angle. But that angle is the same as this angle. It just follows from the figure. So we need to find out sine 180 minus V. That's this red angle here. So that means it is the y-coordinate of this point. So sine 180 minus V is just the y-coordinate of that point. But the y-coordinate of that point is the same as y-coordinate of this point. And what is the y-coordinate of this point? Yeah, here we have an angle of V. So this is just sine V. So here y-coordinate is sine V. So this here is just the same as sine V. So that follows from this figure. That means we have A times sine V. That way we can calculate the area. And the area is the height times the base times a half. So we have the height times the base times a half. But the height here we have expressed now, like this. So we can replace that or substitute in here. That's A sine V times B. Or written in different order, A, B, sine V. But that's just the formula we wanted to prove. So now we have proved it for all angles. And that concludes the proof. Another theorem we can now state using trigonometry. If we have an arbitrary triangle with angles alpha, beta and gamma, and the sides A, B and C, so we see that A is opposite to alpha, B is opposite to beta and C is opposite to gamma. Then the theorem says that sine of alpha, if we divide that by A, then that's the same quotient as if we take sine of beta and this and divide by B. And also the same as if we take sine of gamma and divide by C. So all of these three numbers are equal. So that's the content of this theorem. So let's take an example. Let's say we have this figure. Now we want to find out what x is. Then we can use this theorem. So we take the involved are these two and these two. So if we take sine of 25 degrees and divide that by x, then according to this theorem that should be equal to sine of 70 degrees divided by 8. So this follows from the theorem. And now we just can solve for x. So we multiply up with x and divide up over other things to the other side. Then simple algebra gives us this. And this here now we can just use a calculator to calculate. So, and if we do that, we get this to 3.6. So the side x here must be 3.6. So here we have our figure. Now we can use the previous theorem we just proved. And it says that the area of this one. So let's take first these two sides and this angle in between. It says the area is a half b times c times sine of alpha. This formula we just proved. But similarly, we could just choose other sides. I could take, for example, a and c here. So it's half a times c and the angle in between there, sine beta. Or the third alternative, these two sides. So this is half a b sine of gamma. All these three are just three different ways of calculating the area. Let's now take these two. We say both of these are equal to the area, so we can put these equal to each other. So the first and the second. Then we have half BC, this one, equal to the second one. And if we now multiply away 2 here, and we see that we can divide away c, then what remains is this. And if we divide both sides by AB, we see here that B cancel, and we're left with sine alpha divided by A. This is A, not alpha. And then here A cancels, so we have sine beta divided by B. So now we have proved the first part of the theorem, this part. And if you want to prove the other part here, we can just do the same way, take the second and the third and divide. But let's skip the here, we can leave it as an exercise. But it's just to do the same thing as we did here, then the other follow. The final example of a theorem we will look at is this. So if you have a triangle with sides A, B, and C, and the angle here between two of them we call gamma, then we have the following formula according to this theorem. So the length square of this one is equal to the length squares of these two added, but then minus 2ab cosine the angle. Note that if this cosine is 90 degrees, then we have cosine 90 degrees here. And what is cosine 90 degrees? If we look at the unity circle, just make a rough sketch, the 90 degrees we're up here. So we have to the x-coordinate of that point, but that's 0. So this is 0. So the whole thing here disappears if this is 90 degrees. We're only left with the first part. But that's just Pythagoras' theorem. So when this is 90 degrees, we will get Pythagoras' theorem as a special case of this theorem. So this theorem is like a generalized version of Pythagoras' theorem. So that could just be interesting to note first. But now we don't have to stick to a right triangle. Now this could be anything. Then this formula holds. And let's take an example of that. So let's take the following figure. So we take this triangle here. It's almost right, but not really. So then we can use this theorem. So we want to find out x. Then we see that we should take a squared plus b squared. We should take squares of these two sides. So 5 squares plus 10 squares. And then minus the double product times cosine for 85 degrees. Okay, and this we can calculate. 25 plus 100. This is 100 cosine 85. And now you can just take the square root on both sides. This is 125 minus 100 cosine 85. And plugging this into calculator, since we have to calculate this with the calculator, this gives us 10.8. So this side is roughly 10.8. So here we have our triangle, and here I just put an height of the triangle like this towards one of the sides here, B. Let's call the length of this one B1, the length of this part for B2. Now pure calculation will give us the result. So if you want to take now c squared and just start to calculate, what do we get then? C squared, that is h squared plus b2 squared according to Pythagoras theorem. So this squared plus this squared is equal to this squared. And now, what can we do now? We look at the other triangle, also a right triangle here. Then we see that h squared plus b1 squared is equal to a squared. And here we can solve for h squared, and then we have a squared minus b1 squared. And let's replace this one here. That gives us a squared minus b1 squared plus b2 squared. But then b2, we can write that as b, the whole thing, minus b1, this part. So b2 is the whole thing minus this part. If then we take the square of a difference, if you don't remember the rule for that, you can look up here. So take the square of a difference here on this one, this parenthesis. What do we get then? Keeping the first two intact, this will be b squared minus the double product plus b1 squared. So now I just written the square of a difference. Now we see that this cancels to that, so we are left with this. But let us now replace b1 here. So if you look at this figure here we have a right triangle. If I take cosinus of this angle, what's that? That's just this one, b1, divided by a. And then I can solve for b1. I can write this a times cosine gamma. But then I can just substitute this here for b1. And what do I get then? Well, I get a cosine gamma. And just tidy it up a little bit. We see that we have arrived at our result because we can change the order here. And this is the result we are looking for. So thereby we have proved the theorem.